Let's take a look here at some of the special properties that come up with sound specifically. So these are things that we care about a lot with sound, properties of the waves. So first is the Doppler effect, and what's going on here is that the frequencies, I shouldn't say frequency, the frequency, or if you want to think about it also as the wavelength, you can. But mainly we think the frequency of sound changes if the source and the observer are moving relative to one another. So we see an example down here of there's these two observers, the person on the left here, the person on the right, and the car moving in the middle. The car is producing the sound, and the Doppler effect is what we see happening to the waves. So if you notice, this first, the one position down here, you can kind of see my pen, and the one wave, that circle shows you how far the wave has reached by the time we're at some point later. Same thing with 2, 3, 4, and 5. So as it moves forward, the waves go out, and what you end up noticing is something interesting where in front of it, these waves are a little bit closer together, and behind it, they're a little bit farther apart. And so what does this mean, practically speaking? Like I said, we're going to imagine that car, and there's a siren running. So the waves that are in front, the waves that go out in front of the car, those are then chased by the car, right? The car is following after those waves. And so what ends up happening is, we'll say they pile up. So I send out a wave, I run after it, I send out another wave. Those waves are naturally going to be closer together, or the peaks, the high pressure zones are going to be closer together. That means the wavelength is shorter, and the frequency is therefore higher, because remember, wavelength and frequency are going to be inversely related. The waves that are sent out of the back of the car, those are being run away from, right? I send out a wave, I run away, I send out another wave. And so those are going to spread out. This means that the wavelength is longer and the frequency is lower. So that kind of classic like zoom by sound that you have in your mind when a car flies by, that's the Doppler effect. It's higher pitch as it's approaching you because it's piling up all those waves and continuing to send them out. And then once it goes by, it goes down to that lower pitch. And so that's the Doppler effect there. Related to that, we have sonic booms. So if something is traveling so fast that it's faster than the speed of sound, then rather than just increasing the frequency of the sound, we actually pile up those waves completely, and we get massive constructive interference. So we just get a really loud, really high pressure air, really high sound. So again, if you imagine you've got your object, so it's flying along, and if it's moving and it's sending out those waves, just like in that last picture, we've got like a wave, but if it's moving faster than the speed of sound, then that means all these waves are essentially being emitted from the front. And what you notice is there's all this air pressure piled up out front. And then as we have these cones going back, that's what we call the wave front. And this is the really loud part. So you'll actually see, like if a person's standing underneath whatever this object is, say it's a plane, they'll see it fly by them, and then a second later they'll hear the boom as this pile up finally reaches them. This is a little, the details of it get kind of complicated fairly quickly, but you can just think about it, same idea as the Doppler effect, but you're going so fast that rather than just getting the pitch higher, you just make one giant single wave, so it's just a big boom. The last thing that we're going to look at here is, or the next one we're going to look at here is beats, and this is if two sounds are close in frequency, then they go through rapid constructive and destructive interference. And so they alternate between loud and soft. So if they're really close in frequency or really close in wavelengths, you see these two waves down here, wave 1 and wave 2. And if you look at the beginning, they look like they're identical. But as you go along, eventually you realize about, let me switch to red so it shows up on the white here. When we get to about here, you notice that suddenly they're off because they're ever so slightly different. And so as time goes on, they get farther and farther off. And then what you see here now is we have an up and a down that are canceling out. And then we see at the bottom here, we have it be twice as loud, and then it gradually gets to, quite soft. And then as time goes on, because they're ever so slightly off, they continue to shift back until they're kind of back in alignment. And they shift some more until they're back out of alignment. And so we get this warbling effect, this wah 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 sound. So if you've ever played an instrument and you've tried to tune it by listening, you'll know this. You'll have experienced this, and you'll know that you're getting your notes more in tune with each other as those beats get longer and longer. So if it's really warbly, you know you're way off. As you get closer, you know that it's more accurate. And so what we say are the closer the frequencies, the slower the beats. So again, as they get closer and closer, it takes a really long time for them to fall out of sync, and it takes a really long time for them to get back. So that warbling is a lot slower and a lot less pronounced.